Reaching the surface of Venus requires sheer, brutal engineering. We build machines knowing the planet will quickly crush and melt them. Scientists once held a much gentler view of our neighbor. In the early 20th century, the prevailing belief was that Venus was a lush, tropical twin Earth hidden beneath a permanent layer of clouds. The reality was much harder to see. Looking from space revealed nothing about the conditions below, as the planet is wrapped in a thick, featureless shell that acts as a total physical barrier to our telescopes. To find out what lay beneath, the Soviet Union launched the early Venera probes. These spacecraft began the descent through the clouds, but the weight of the atmosphere destroyed them well before they could reach the ground. Reaching the surface demanded a brute force suicide mission against the laws of physics, an engineering feat so extreme it remains unreplicated today. Telemetry revealed a surface pressure 90 times greater than Earth's. The carbon dioxide acts like a supercritical fluid, exerting physical weight comparable to a deep ocean trench. Temperatures hover at 465 degrees Celsius, hot enough to effortlessly melt solid lead and aerospace electronics. Soviet engineers optimized their designs for a limited shelf life, building machines to function briefly before the environment inevitably consumed them. To buy that precious time, the Venera landers relied on a heavy, dense, and unmistakably rugged design. The core utilized a double-shell pressure vessel. Inside this titanium armor, engineers packed phase-change materials, chosen to absorb incoming heat by melting internally, shielding the payload. Insulation alone wasn't sufficient. Mission controllers actively pre-chilled the entire lander to -10 degrees Celsius before it detached from the cruise stage, giving the craft a cold thermal starting point. Every ounce of the lander's core functioned as a thermal battery in reverse, banking cold to delay the inevitable moment of thermal death. The descent was a harrowing plunge through clouds saturated with sulfuric acid, a corrosive environment capable of dissolving standard alloys as the craft fell. Engineers faced a difficult choice: use parachutes to slow down and risk being cooked by the heat, or fall fast and risk a catastrophic impact. They chose speed. High in the atmosphere, the craft ejected its parachutes and utilized a wide, rigid metallic disc called an aero brake to stabilize a high-velocity freefall through the dense, lower gas. This strategy accepted terrifying g-forces and massive velocity as a necessary trade-off to reach the surface before the heat could penetrate the hull. At the bottom of the drop, the lander slammed into the surface at over 7 meters per second. Rather than using delicate legs, the craft rested on a massive, hollow metallic landing ring. This data shows the load deflection during touchdown. The hollow metal ring was designed to permanently deform upon impact, absorbing the kinetic energy and preventing the lander from bouncing or tipping on the rocky terrain. Upon contact, a frantic sequence of automated experiments began. The environment made every movement unpredictable. On Venera 14, the soil drill deployed perfectly, but landed directly on top of the camera's ejected lens cap, blocking the analysis. Years of development yielded a narrow 120-minute window of operation. The landers had to transmit every byte of data before their internal components finally succumbed to the heat. These processed panoramas are the result of that engineering sacrifice, the first and only views ever captured from the surface of another world. The visual data reveals a world with a flat, orange-tinted sky. Jagged basalt rocks litter the ground, providing clear evidence that Venus is an active, geologically volatile planet. The landers also recorded acoustic data. For the first time, we heard the low, heavy roar of the Venusian wind moving across the sweltering plains. Because of these sacrificial machines, we possess a brief, ground-level connection to a planet that is otherwise hidden from view. We haven't returned to the surface because modern silicon-based microchips are highly sensitive to heat. They fail far faster in these extremes than the rugged, old-school vacuum tubes used in the 1970s. New missions like DAVINCI and VERITAS are now in development, designed to probe the atmosphere and map the surface in search of the answers the Venera program first suggested. Yet the original pioneers, those distorted, semi-melted titanium hulks, remain there to this day, resting silently on the volcanic rock. If you want to see more on how we explore the most extreme environments in the cosmos, subscribe and activate the bell for TEMBODocs. The Venera program demonstrates that reaching the most hostile corners of our solar system sometimes requires engineering a machine purely for its own magnificent destruction.